And as a start, for whatever reason, I want to make sure that you're reading these correctly. A sub 1, A sub 2, A sub 3, A sub n. Sub, S-U-B. Sub goes below the water. These are subscripts. So that these numbers 1, 2, 3, 4, and the letter N are below the letter A sub, and then whatever the number or letter is. It is not S-U-B. I'm not saying sub. It's not a B, it's a B. So if my articulation is not clear, this is what I mean, not this. Everybody clear on that? These are subscripts, no mathematical value whatsoever. Today we're going to be very, very, very specific on what kind of sequence we're looking at, and we're going to be very specific on the formulas that you can use with that sequence. So this is any sequence in general, a sub n minus 2, a sub n minus 1, a sub n plus 1, a sub n plus 2, and it continues on. This is a general way to identify any terms in the sequence. N has to be a positive integer. So if n is 10, this is a sub 10 in the middle. 10 plus 1, this would be a sub 11, a sub 12. 10 minus 1 would be a sub 9, and a sub 8, etc. Sometimes you'll have a starting amount of a sub 0. That's only for application problems, and it's not a major concern for us for a couple more days. So you shouldn't worry about any a sub 0s. If you have a tutor, some tutors teach restart everything with a sub 0. If you go to Oakmont High School and you're in Algebra 2 and you're doing sequences and series, they start everything with a sub 0. I've always used a sub 1. The majority of the reference materials you'll find will use an a sub 1 for the first term. And when I was at Oakmont teaching it, it was really confusing. And I don't know if I was more confused or the kids were more confused because I was. So we are starting today, we are talking about this very specific type of a sequence called an arithmetic sequence. In an arithmetic sequence, the difference between any two terms, any two consecutive terms is a constant. The variable we use for the constant is called d. And you have to take the difference from any term minus the previous term. The order is important here for finding d. Any term a sub n minus the term prior to it, which would be a sub n minus 1. A sub 12, subtract a sub 11. A sub 53, subtract a sub 52. So when you look at these sequences, there's several examples here. First thing you want to do is say, is the first sequence arithmetic? Is there the same thing being added over and over and over again, or subtracted over and over and over again? Yes or no? Yeah, this is a hard one. To get from the first term to the second term, what are you doing? Thank you, adding 1. So take any term and subtract the previous term. 4 minus 3, 3 minus 2, 2 minus 1. The common difference, d, is going to be 1. How about the blue sequence? Is that an arithmetic sequence? Yes. What's the common difference? 2. How about the purple sequence? Common difference of 5. How about the green? Now, it's really important that you recognize that it's 7 minus 10, 4 minus 7, 1 minus 4. The common difference is a negative 1. Or, excuse me, a negative 3. It's negative, not positive. Don't do big number minus small. What's the common difference here? So what's the common difference? There isn't one. And why isn't there one? So it's not an arithmetic sequence. Right? You have to make sure it's arithmetic first before you started identifying the common difference, either plus 3 or plus 5, plus 7, and saying, well, we're adding something, it's just not the same thing. This last one right here, not arithmetic. So we don't even worry about that today. Just say it's not arithmetic.
What's the green one?
Negative 3 is the common difference. Subtract 3, subtract 3, subtract 3. 1 minus 4 is negative 3. 4 minus 7 is negative 3. And 7 minus 10 is negative 3. Does that seem logical? In an arithmetic sequence, to get to the next term, you have to be adding or subtracting the same thing over and over and over again. Okay? And you can look at it as adding or subtracting. You can look at the sequence and say, hey, I'm subtracting 7 each time. I'm adding 3 each time. One like this, you'd say it's not arithmetic. It's the power of 3. 3 to the 0, or 3 to the first, 3 to the second, 3 to the third, 3 to the fourth. Not an arithmetic sequence. So the difference between two terms, two consecutive terms, is called the common difference. We use a lowercase d to represent the common difference, and you find it by taking any term a sub n and subtracting the previous term a sub n minus 1. So when you look at a sequence a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, a sub n minus 1, a sub n plus 1, dot, 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 any two terms, consecutive terms, take the one on the right, subtract the one on the left. 17 minus 14, 23 minus 20, 11 minus 8. Doesn't matter which two you pick. Take any term, subtract the previous term. So your common difference is found by taking any term, subtract the previous term. I'm telling you right now, some of you are not going to adhere to that. You're going to do the big number minus the little number that are next to each other, and you're going to screw up the sign of the common difference. It's got to be some term minus previous term. A sub 5 minus a sub 4. Okay? We're going to look at this sequence, and we're going to break down how the sequence is generated. It's well worth seeing this so that you get a feel for where this next formula is coming from. So I just picked a pretty basic arithmetic sequence, 4, 9, 14, and 19. And my first term, a sub 1, is going to be 4. How do I get to the second term? Add 5 to the first term. So we're going to take the 4, and then we're going to add 5. How do you get to the third term? To what? To what? Which is? No. No, I'm trying to ask you obvious things. What's this and what is that in the sequence? And sometimes we would call it the first term. What is this? And it is 9. Okay? And how do we get to the third term? You add 5 to the second term. So the second term was 4 plus 5. And we're going to add 5 to that. How do we get to the fourth term? Add 5 to the third term. Here's the third term, plus 5. look at these things, kind of break them down a little bit. All four of these expressions that I wrote for a sub 1, a sub 2, a sub 3, and a sub 4, all four of them have something in common. What is it? They all have a 4 in it. So we all have a 4 in each of these expressions. And 3 of the 4 have 5s in them. And if you break this down and we look at how many 5s are in the fourth term, there's 3 5s. 2 5s in the third term, and 1 5 in the fourth. And we're adding those. And technically we could say that there's 0 5s being added in that first term. Does everyone see this pattern developing? Anyone not seeing where these numbers are coming from? Now what we want to do is we would like to take and find the relationship between this number and this number. Here and here. 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 See if we can't determine the pattern that develops in those situations. What do you notice between the number of 5s and the position of the term itself? It's 1 less than the position. 2 5s for the third term, 3 5s for the fourth, 1 5 for the second, etc. What's 4? The number in red. It is the first term. And what's 5? Common difference. So in general, if I want to find out the nth term, I got to have the first term, a sub 1. I got to have the common difference 5, and I'm going to add it n minus 1 times. A sub n equals a sub 1 plus n minus 1 times 2. That is called your arithmetic explicit formula. It is your fallback formula. When you need some piece of information for a sequence, this is what we use. What's the explicit formula for? In general, it finds any term in the sequence. It will find any term in your sequence. You need the 99th term, use your explicit formula. That's what it's for. What kind of a sequence is this? Red here. What is it? Arithmetic. What else? It's not finite. How do you know it's finite? It ends at 4,999. So there's two kinds of questions I can ask you. The first one I could ask you is, what is the explicit formula for the sequence? And if you want to learn your formulas and have them really well ingrained in your brain and how they work, tonight, on every single homework assignment question, write down the formula that you use. Every single formula you use tonight, write it down, plug it in. Write it down, plug it in. It will not take you more than a couple of minutes longer to do that. But you will finish the assignment totally dialed with the formula. So on this problem, I'm trying to write the explicit formula. I write it down in general. A sub n is equal to a sub 1 is 4 plus n minus 1. Common difference is. Now, with an explicit formula, you have to simplify. So now you're back to your algebra skills. 4 plus 5n minus 5 is going to be 5n minus 1. That's your explicit formula. How do you know you did it right? How do you know this is the correct explicit formula? What could you do, Emma? How could you check it? Sure, so which term in the sequence do you want to check? It doesn't matter. 4. So you plug in a 4 for n. 5 times 4 is 20, minus 1 is 19. That looks pretty good. Easy, easy, easy to check. The position. N is the position, right? So pick whichever number you want to talk about where you know the position. First, second, third, fourth. Plug in one of those numbers. N is 3. 5 times 3 is 15 minus 1, 14. Looks good. It only takes a second. Now, the other question they're going to ask you is, well, what term is 4,999? Again, you're going to utilize your explicit formula. Is equal to a sub 1 plus n minus 1 times d. If you write the formula down every time, and then you plug into the formula, by the end of the homework today, you'll have this dial. What should I put in for a sub n? What's a sub 1? 4. N is what you're looking for, and d is 5. Now, there's a couple of options you have on what to do in this and solving it. I usually subtract the 4,995 equals n minus 1 times 5, and I typically divide by the 5. There's a lot of people who will distribute, which is perfectly acceptable. I usually just divide both sides by 5. When you divide by 5, you're going to get 9,999, if I'm not mistaken, equals n minus 1. And n ends up being 1,000. So 4,999 is the 1,000th term.
So suppose we already found the explicit formula.
Arithmetic. Then I would have used this. So I would have taken the 4,999 and plugged it in right here. Does everyone understand that question? Because it's a really good question. If you know this explicit formula that's simplified already, there's no need to use the general explicit formula. Take the 4,999 and simply plug it in right here. 4,999 equals 5n minus 1, and solve from there. You're going to get 5,000 equals 5n, and n is equal to 1,000. You won't always have to do both of those things, however. So I wanted you to see it the other way. But if you know this formula, this is the way to go. Absolutely. Everybody good on this example? Okay, try this example. Same two questions. So when you're finding the explicit formula, what did you plug in, Ellie? Negative 21 plus n minus 1 times 12. Again, that common difference, it's easier to find doing 15 minus 3 than it is to doing negative 9 minus negative 21. A lot of us make that mistake with the negatives. We had it last period. I don't know if anyone made it here and got a negative value instead of a positive. So when we simplify negative 21 plus 12n minus 12, how did it simplify, Ellie? A sub n equals 12n. Yeah, and I would typically write it this way, but you won't get marked down if you do it the other. But in Algebra 2, at this point, we should have everything in descending order. So 12n minus 33 would be the best way to write it. Now, we'll talk more about this as we progress through, But notice where the common difference ended up in our explicit formula. It ended up as being multiplying by n. So put down in the back of your mind that when the number times n is where your common difference is going to end up. And that's going to be important in our sigma notation later on. Okay, over here, if we do the 651 in for a sub n, what do we plug in for a sub 1? Negative 21. We're looking for the position, that's n. And again, that common difference is 12, not negative 12. So if you add the 21, 672 is going to equal n minus 1 times 12. Now when you're looking at this sequence, it's all integers. What can you tell me about 672 and 12? If you're all integers, no fractions. What do you know about 672 and the number 12? Better be divisible by 12. If 12 doesn't go in evenly here, and these are all integers, you screwed up when you added your 21. Something got messed up. What's 672 divided by 12? 56. Equals n minus 1, and n is 57. You know what my most common wrong answer is? What do you think the most common wrong answer is for this? 55 is second most, oddly enough. 56. People get so excited when they divide it by 12. They're on the calculator, hey, 56, I'll take it. And then they forget to add the 1. And sometimes they subtract 1 to get the 55. But 56 is a very common mistake answer. Any questions on these? Explicit formula is pretty straightforward. Now I put on a few pages of notes here that kind of reiterate what I've been talking about. There's a lot of general notes as well. These are from Mrs. Kraft and talks about a lot of stuff, a lot of examples. You can go through these if you're so inclined. So you're welcome to look at these notes. It gives you some extra practice with them in a different teacher's presentation. Let's skip that. Finite. This sequence is finite. This sequence is infinite. Infinite sequences have no last term. That's how you tell. It has nothing to do with dot, dot, dot. It has to do with having a last term or not having a last term. Finite sequences, or finite, as some of you would say, finite sequences have a last term. So when you look back at these examples, 59, 68, 77, 86, dot, 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 it ends at 284. That's finite. This one, 81, 78, 75, 72, dot, 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 that means it goes on forever, and it doesn't have an end. That's infinite. Now, I want you to understand, today, everything we do is arithmetic. You guys are going to think this homework is a breeze. You're going to walk through it like, wow, what was he talking about saying this stuff is confusing? Just like last chapter. Nothing was confusing until you put it all in the same box. And you pull out a problem and you go, dude, I have no idea what kind of problem this is. So this is the chocolate candies at Christmas with no labels. How do you find out what kind of candy you have? Well, you have to bite off the bottom. And if you like it, swap it in. If you don't like it, you glue them back together and stick them back in the box. Right, Christo? Oh, yeah, right. You've never done that. I know how it works. If you can't tell the difference on Wednesday, you're in trouble. So I say this today, which is, yeah, this is a no-brainer. Infinite arithmetic sequences have no sum, ever. But it has to be infinite, and it has to be arithmetic. Come tomorrow, that's not going to be true all the time. And on Wednesday, when I give them to you with no labels, you better be able to tell the difference. So if it's arithmetic, it's infinite, there's no sum. It doesn't matter what you're adding over and over and over again. If I send each of you out to your favorite beach in the world, wherever it is, and I ask you to bring me a grain of sand from that beach, and I want you to put the grain of sand on this table, and I want you to keep going back and forth from the beach to this room forever. You can keep bringing grains of sand, one at a time. What's going to happen? Really? When? I said forever. There is no end in forever. You're never going to end. If you die during this process, your quest goes to your children, and their children, and their children. Yes. This isn't real. We're not really going to do this, boys and girls. We're not really going to your favorite beach and bringing one grain of sand at a time. But if we did, what would happen? Yeah, but what would happen here? The room would fill with sand, then what? So then what? Yes, we have to put the sand here. So then what? Fill up the other rooms. Fill up the campus. Fill up the town. Fill up the state. We would have an infinite amount of sand and we would never come to an end. What's that?
You would run out of data.
No, there's infinite supply. We'll send Bruce Willis out onto a rock out in space and they'll crush it up to make more sand. Forever. Okay? If it's arithmetic, no matter how small what you're adding is, if it's infinite, there's no sum. Okay? Can we talk about Freddie Gauss? Little Freddie Gauss and his elementary school teacher. Years ago, this famous mathematician, the elementary school teacher, I don't know what her deal was, but she decided, I don't want to teach today. So she told the kids, take out your math chalk or whatever that you're going to use, and I want you to add up the first 100 numbers from 1 to 100. Ready to go. And then she went back to her desk thinking, I'm going to get myself a little nap. Like a minute later, here comes little Freddie Gauss. He walks up, bam, here's my answer. And of course, it's correct. It's like in 2nd or 3rd grade or 4th grade, whatever it was. Almost a minute, and he's got the answer. Didn't have those calculators that you guys have. All the other kids were doing 1 plus 2 plus 3 is 6, plus 4 is 10, plus 5 is 15. Not Freddie. Freddie, he's got a t-shirt just like you guys. Yeah. But he also has another t-shirt on the other side. It says S. You know what that is? Smart. How do you do it? You know this one? If like.
Okay, so 1, if you add it to 99 is 100, 2 plus 98 is 100, 3 plus 97, 4 plus 96, and then you get to the middle, 49 plus 51, and you just keep going.
So how many groups of 100? 49 groups of 100. For 4,900, right? What did we not count? 150, 1 at 50, and 1 at 100. And when you add those up, you get 5,050. No calculator needed. Now, I don't know that that's what Freddie did, but something like that. Okay? That's really good. Really good way to go. I think, at least the way I'm going to tell the story is what Freddie did was he said, look, I'm going to pair them up like this. The 1 in the 100, the 2 in the 99, the 3 in the 98. Bless you. The 48 and the 53, the 49 and the 52, the 50 and the 51. What do those add up to? 101. How many groups do we have? 50 at 101 each is 5,050. Now let's look at this. Where'd the 50 come from? Okay. Divide 100 by 2. What's 100? What's the 100?
Oh, it's the last term.
Yeah, it's not what I'm looking for. It's definitely not the sum minus 1. Sum minus 1 is 5,049.
101 minus 1.
Oh, the sum of the pairs? That's just, yeah, you're giving me things that are coincidental. Where's the 50 coming from? Right? What's that? Yes. So where did we get the 50? Okay, so go back to your 100. There were 100 numbers, right? Where's the 50 come from? This is where you're thinking. Don't let someone else think for you. She's already given you the first part of what you need to know. Where did the 50 come from?
How many pairs of 101?
We got that it's that number of pairs. Take away the 101 out of it because that's unique to this problem. There's 100 numbers. Where did we get 50? What? Just divided it by 2. Okay? I didn't hear you say that. If you said that, I apologize. I heard lots of things about pairs and that kind of stuff. That's not what I'm looking for. Now, what about the 101? Where did that come from? Each pair added together. Okay? Each pair added together. This is going to work for every arithmetic sequence that is finite. Little Freddie has a gift here. Take however many terms you have and multiply it by the sum of the first and the last term. That'll give you that common sum that you got. And then divide your answer by 2. Number of terms times the sum of the first and the last, all divided by 2.
So what is the stand for this?
The number of terms is what it always stands for. N is the position of any term in the sequence. If you're trying to find the S sub n, S sub 6 would be the sum of the first 6 terms. So for Freddie's problem, how many terms were there? 100. So we're going to do S sub 100 is going to equal 100 terms times the first plus the last over 2. Now, either n over 2 or a sub 1 plus a sub n over 2 will be divisible by 2. Sometimes both of them are. But one of them will be for sure. And what you need to know is that this formula works for any arithmetic sequence that is finite. As long as you only want to find a finite number of terms for the sum, you're good to go. If it's infinite and it says find the sum of the sequence, can't be done. If it's finite, good to go. Don't even need to know what t is. Doesn't matter. So here's a sequence. If that sequence looks like that, and I say find the sum of the sequence, find the sum of the terms of the sequence, what are you going to say? You can't. There's no sum exists, is what you're going to say for an answer. No sum exists. Or the sum is infinite. But I would say no sum exists is better. Now, I want you to find the sum of the terms in this sequence. Remember, n is not 5 for this sequence. If you start to find the sum, s sub n is equal to n times a sub 1 plus a sub n all over 2. That's the formula you want to use. When we're finding the sum, a sub 1 is negative 21 plus a sub n 651 all over 2. That's not a problem. The problem is we don't know what n is. Where are you going to get it? The explicit formula. So whenever you're missing information, you go to the explicit formula and you can get it out of the explicit formula. It's a piece of cake. 651 equals negative 21 plus n minus 1 times 12. So we did this earlier. Oops. When I add 21, I get 673 to 1. This is a Monday. So let's try again. 672 equals n minus 1 times 12. When we divide it by 12, it's 6. And when you add 1, you're going to get n is 57. That's what we're going to plug in right here. Any questions on getting to that point? Anyone not seeing it? So when you simplify here, 57 times, when you add negative 21 and 651, you're going to get 630. And as I said, one of the two numbers in the top, either n or a sub 1 plus a sub n, will be divisible by 2. When you multiply and divide by 2, what do we end up with?
17,900.
That's the sum of the terms in this sequence. This question is written kind of like the first one with Freddie, where I'm saying, find the sum of the first, now I'm telling you 35 terms. And I'm telling you the beginning of the sequence, just like Freddie knew. So Caitlin, what did you plug in on this one? A sub n, that's the term we're looking for, 14 plus,
N minus 1.
what'd you put in for n? What term are we trying to find? So what should I put in for n? 35 minus 1 times, fantastic. So you can see that everything's plugged in now except for a sub n, which is what we're looking for. So 14 plus 34 times 3 will give you 14 plus 102. And 14 plus 102, how much? 116. That is a sub 35. 35th term. Remember, keep focused Didn't want to know what the 35th term was. Don't get too excited. Great job. Not what I'm asking for. I'm asking for the sum. So don't put 35 as your answer. The sum, again, write the formula down every single time, and you'll know your formulas by tomorrow. But you want to write them down because the formulas tomorrow that we do, there's an explicit formula, there's a sum formula. And the patterns are kind of similar. So you want to make sure you're dialed in. This is sum of an arithmetic. Rachel, what'd you put in for n?
35.
A sub 1, a sub n, all over 2. So you have 35 times 120 all over 2. What'd you get for your final answer, Rachel?
130.
Sorry, 130 here. How much?
200.
Thank you. So the sum of the first 35 terms in the sequence is 2,275. Anyone not following the process steps? You need to understand no work and it's no credit. It's not partial credit, it's no credit. So you have to go through the process of solving this algebraically, and I need to see it. You have to go on this side with the sum and show me the plug-in and simplify. Okay, this is not negotiable. You may not find the 35th term for credit by going 23, 26, 29, 32. Believe me, every year I have one kid in each class. You look at their work, all they have is the whole thing written out. And then the honest to God truth is, they add up all 35 terms on the calculator because they have no clue what's going on. If you do that, you're going to get nothing for points. So, gotta know your formulas. It's not the answers I really care about. You don't really think I care about the sum of the sequence. You don't think I'm going to go home and say, you can't believe this. Check this out, what they did in class. They found the sum of this sequence. My boys will be like, wow. My boys will not care. Neither will my wife. And neither do I, and neither do you. Okay? This is a blankety blank problem. You're better off trying to show everything than to impress me with what you can do in your head. Blankety blank problem. The sequence looks like this. Blank, 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 24. Blank, 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 384. And this is a sub 4 in the real world. And this is a sub 8. Okay, remember we talked about Mr. Rogers' world? Did we do that last week?
No.
Must have been in the honors class. Okay. How many of you watched Mr. Rogers when you were kids? Okay? I love Mr. Rogers. Okay? This guy was as laid back as they come, right? I loved when he was in the living room and he had the little, remember the little trolley? Trolley? Where did trolley take you to?
His neighborhood.
No, he's in his neighborhood. But where? No, it took you someplace specific. It was a land. Where did trolley take you? To the land of make-believe. Okay? And in the land of make-believe, all kinds of things happen. Here's what we're going to do in our land of make-believe. We're going to pretend that 24 is a sub 1. And that would make 384 a sub 5. Does everybody follow what I'm doing here? In green, we're going to pretend that a sub 4 is really a sub 1, and a sub 8 is really a sub 5. The question for this is going to be to find the first term. In the real world, here's the first term way over here. And I know you might be able to guess and check your way back to that, but that's not what we're interested in. So what I want to do is in the land of make-believe, I'm going to come over here and I'm going to say, okay, in the land of make-believe, the last term is 384. The first term is 24. The number of terms is, excuse me, what's the number of terms? 5. But we don't know the common difference. So we are going to figure out what that common difference is. We're going to subtract 24 and get 360. It's going to equal 4D, and D is going to equal 90. Now I know that you could use the 90 and count back to find a sub 1. It's not going to fly. Because if I give you a sub 400 and a sub 408 and said, I want you to find a sub 1, you're not going to count back from a sub 400. Well, most of you won't. Stephen might. No? What I want you to do is come back over here into the real world. When trolley brings us back, come back over here and use the explicit formula for the real world now. Now, it doesn't matter whether you use the 384 or the 24. Which one do you think you should use? It doesn't matter. Why? Smaller. It's easier. Put that in for a sub n. What do I plug in for the first term? Nothing. We just leave that a sub 1. That's what we're looking for. For 24 in the real world, what's n? 4. Minus 1, and we already discovered what d is over here in the land of make-believe. That's 90. Now you're back to a basic algebra problem. Very basic. We're solving for a sub 1. 24 equals a sub 1 plus 3 times 90. 24 is equal to a sub 1 plus 270. When you subtract the 270 from both sides, you're going to get a negative excuse me, 246 is equal to a sub 1. Any questions on that? So the answer to this question is going to be negative 246. That's what you're looking for a sub 1. Again, I know that you could have used the 90 and counted back, but I'm not going to give you credit for that. It's not the point of what we're doing. The point is to be able to use the formulas to get what you need. If we want to make problems that are really, really complicated to prevent you from doing that, we could do that. We're not. We're going to use problems that are pretty basic.
Why do you use 4 for n on the second?
Because we're back to the real world in blue right here. So if I'm putting 24 in for a sub n, what's n? It's got to be the 4th spot. So in green here is what I did with the land of make-believe. In that case, the 24 was a sub 1. And n would be 1. But for 384, the n would be the 5. N is always what position are you in, whereas a sub is always the term itself. Anybody else see any confusing things? Before we lose Corbin here? We're all good? Right, so the last thing I want to do is specifically focus you on the sigma notation for arithmetic sequences. So this is only arithmetic. Now, there's sigma means to find the what? What is sigma telling you to find? Sum. So your sum formula, S sub n equals n times a sub 1 plus a sub n all over 2. There's 3 things you need to know. n, a sub 1, and a sub n. Here's how you find the sigma. A sub 1, plug in the number on the bottom. You want to find a sub 1, plug in the bottom number. What's the bottom number on this sigma? 5. When you plug it in, when I say plug it in, you're plugging it into your explicit formula right here. This highlighted formula that's to the right of the sigma is always your explicit formula. Always. So you're going to take the 5 and plug it in right here. What's a sub 1 going to equal? 11. Would have expected more of a choral response on that. Is anyone not seeing where the 11 is coming from? The bottom number is 5. Plug it in to the equation, the expression right here.
So it's
3 times 5 is minus 4, 11.
is it just 2 that's the same top number?
Must be. What would you plug in to find the second term of the sequence? 6. What would the second term of the sequence be? What would you plug in to find the third term of the sequence? 7. And you would get 17. So a sub 1 is found by plugging in the bottom number. A sub n, better known as the last term, is found by plugging in the top number. When you plug in the top number, what do you get? 29. Is anyone not seeing the 29? Anyone not seeing the 29? Yes. A sub n, plug in the top number. What number is on top of the sigma? And when you plug it in, 3 times 11, 29. And if you wanted to write out the whole sum, the whole summation, you would do 11 from plugging in the 5, then you plug in a 6, plug in a 7, plug in an 8, plug in a 9, plug in a 10, and you would have that series that you would add up. And I'm not suggesting you do that, I'm just telling you to write out sigma notation in expanded form, that's what it would look like.
What is it meant by like the top number minus the bottom number?
I haven't talked about that yet. Doesn't mean anything right now. But I don't want you to add up these numbers. I want you to use our formula. So when we're using the formula, I want you to say, plug in the bottom number, that gives you a sub 1. Plug in the top number, that gives you a sub n. And then to find out how many terms there are in the sequence, take the top number, subtract the bottom number, and add 1. What do you get when you do that? 7. That's how many terms there are in the sequence. Top minus bottom plus 1. So when we want to find the sum, we're going to take the top minus the bottom and add 1, that's 7. We're going to take the first term, which we found by plugging in a 5 in this problem, get 11. And we're going to add to that the last term, which we plugged in an 11 to get a 29. And we're going to add those and divide by 2. Does everyone see where the 7 comes from?
So the 11 in the formula, or in the sigma, is it's the last term, and then the 5.
The last term is 29,
What's the 11 then?
the top number.
I know, but like, why is it there?
It can be anything. In this particular problem, it's there because I typed it there. There's no magic. You're looking for some overlying reason. Doesn't exist. Could have been a 54 for this problem.
Okay.
I just picked 11. It's a total coincidence that this is an 11.
Well, yeah, I know. I'm just saying, like, what's the top number mean? Like,
Doesn't mean anything. It's just a number. The only thing it has to be is bigger than the bottom number. Because this is telling you to use the variable k, start the value for k's at 5, end the value at 11. To find a sub 1, you plug in a 5. To find a sub n, you plug in 11. That's it. There's no higher purpose or anything like
You're
that.
saying find the sum between the 5th term and the 11th.
I'm not. I'm saying find the sum of the first 7 terms. This is not the 5th term. This is just a number. When you plug in a 5, what do you get? A sub the first term. You plug in integers from 5 to 11, including 5 and 11. And they generate the first, second, third, fourth, fifth, sixth, and in this case, 7th terms.
But in 12.1, didn't like the top number mean that's as far as you go in the sequence?
That's the last thing you plug in, exactly right. So we start with 5, end with 11.
Okay.
It is, again, not telling you the position unless this is a 1. If that's a 1, there's 11 terms in the sequence.
So are there still like more numbers between 26 and 29?
Nope. You plug in a 5, we got the 11, right?
Yeah.
The next integer after 5 is,
Oh, 14.
okay, listen to my question. The next integer
Oh,
after the number 5 is,
6.
that's what you plug in next.
Okay.
3 times 6 is 18 minus 4,
Oh, I get it. Okay.
that's the second term.
Okay.
The next integer after 6 is 7.
And then 29.
When you plug in a 7, you get 17. When you plug in an 8, you get a 20, 9, 23, 10, 26, and 11. Finally, our last term is 29.
Okay.
So first term, plug in the bottom number. Second term, plug in the top number. To find out how many terms, top minus bottom, plus 1. Can the bottom number be negative? Absolutely. The top number could be negative as long as it's bigger than the bottom number. And they could be zeros. It could happen. So what does the sum end up being here? We end up with 7 times 40 over 2 for a 140 sum. So that means that this expression in black evaluates to 140. It's really important that you understand this because there's a bunch of these problems on the test, and they're really easy, but it's really new, and it's really different than what we do typically mathematically. You can't just look at this and say, oh, it's this. You have to realize what it's telling you. So if you need to have a different explanation, let's try something different. And if not, this is what you're going to do.